Myself Rahul Yuri. Today I am going to discuss my subtopic of communication system, that is Nyquist criteria and sampling theorem. But before that, a question arises in mind: why GATE? So I would like to brief you that how you can shape your career. So you can see by clicking GATE, you can go into various fields by clicking GATE. First one is MTech. Those who couldn't pursue their BTech in ITs, it provides another opportunity to study in institute like ICs, ITs, NITs and ICR. One can also go into PSUs, BHEL, ONGC, NTPC, BEL, BAR and ETC. And one can also go into CSR for PhD. And also one option is also available. One can also go into abroad. NUS, NTU, that is National University of Singapore, and National Technological Universities, National Tangyan Technological Universities also offers MS and PhD courses using GATE scorecard. Now, while wasting much of time, I would like to jump into my topic, that is communication system. I would, before jumping into my topic, communication system, I would like to discuss about the weightage of this subject. This subject covers 10 to 15% of total people. So one cannot leave this subject for the GATE examination. So now we will discuss about our topic, that is sampling theorem, Nyquist criteria. Sampling theorem. So sampling theorem deal with conversion of analog signal into digital signals. That is analog signal into digital. So we follow some steps for converting analog to digital. First one is that so now we will discuss about analog to digital conversion. Okay. So when we convert analog signal to digital signal, our first step sampling theorem. Sampling. So how we do sampling? So, suppose this is a massive signal. So, for sampling, we take samples of these signals and we take equal interval. That is called sampling interval, or also called, this is also uniform sampling. This is massive signal and this is unlimited signal. So for sampling, conversion of massive signal, so we do sampling. We never do sampling for unlimited. Sorry, this is not unlimited. This is unband limited. Signal. So in sampling theorem, we use Nyquist criteria. Nyquist criteria says that sampling frequency must be greater than the 2 times of mass's frequency. So this is the criteria for sampling, perfect sampling. So how we today we will see that how we reach to this. How we can reach to this criteria f is equal to 2fm. So for this, first we will do sampling. So for sampling, we multiply massive signal with impulse train for taking samples of different points. So this is impulse train and centered about 0, TS, 2 TS, 3 TS, and this is infinitely extended, this is infinitely extended, and this is Ts. Okay. So when we multiply the message signal with impulse train, we get samples of different points. So we will discuss about what criteria should be chosen that define Ts. Okay. So mathematically we can write delta of t is equal to summation of n is equal to minus infinite to infinite delta t minus n ts. Okay. So now we will take Fourier transform. Why? Because we see the property in frequency domain. This is the time domain representation of signals. Now we will take Fourier transform. Fourier transform represents the signal in frequency domain. So when we will take Fourier transform of massive signal, it will convert it into this form. This is Fs, this is minus Fs. Fs is the sampling frequency. Okay. Now, but question is that this is unbounded, band limited massive signal. So sampling criteria depends on massive frequency, that is Fs is greater than equal to 2Fm. Okay. If bandwidth of massive signal is infinite, here we can see that massive signal is infinitely extended. So bandwidth is maximum frequency minus maximum possible frequency minus lower frequency possible frequency in masses. So here bandwidth of massive signal is infinite. So we cannot use if we use this signal, we cannot get this criteria because Fm is infinite, then Fs is also infinite. That is, we can see that this is not the practical case because we cannot choose samples. One sample is at 0 point, second one is infinite point. That's why we need a filter that is called anti-aliasing filter. So before going to further, we pass this massive signal into anti-aliasing filter. This is a low pass filter, this is a band limited filter. Anti-aliasing filter. It works. It functions that it's band limited. It's band limited the massive signal, means massive signals, that is band limited, limits the massive signals. So now we can see that now this is band limited, that is this is the FM, this is the minus FM. Now we can use this criteria for selecting the sampling frequency. Okay. So now we will discuss. Now we will see how we get this criteria by using spectrums. So now we can rub it. Okay, so we have discussed one point. Second is when we will take the Fourier transform of impulse train, we also get an impulse train again. That is Fourier transform of this is Fs summation of n is equal to minus infinite to infinite del of f minus n Fs. Okay. So that is 0 point, that is Fs, that is 2Fs, and that is minus Fs. Okay, and this is Fs. So we know that this value denotes area, not value. This is a very important point because Fs denotes the area of this impulse, Okay. So one important question also arises that how we reach from this time domain to frequency domain. So for getting Fourier transform of this impulse, we must convert this signal into Fourier series. So the Fourier series representation of this impulse is given by 1 upon ts e to the power j omega s and t. 1 upon ts and varies from minus infinite to infinite, and 1 upon Ts is actually the Cn, coefficient of Fourier series. So now we will take the Fourier transform. Actually, we takes the Fourier transform of this signal. So 1 upon Ts becomes Fs, that is, when Ts is the sampling interval, F is the sampling frequency, it becomes Ts, and e to power j omega nt, actually this is the shifted version. So we shift the signal in time domain. Okay. So multiply by phasor results in shifting in frequency domain. So okay, now this is the basics. Now we will go into how we get this criteria, which is very important. So when we will multiply it by this, now this is the graphical representation. Now we will discuss about mathematical representation, mathematical equation. Okay, so nt, and this is the impulse train. Now when we multiply it by mt is multiplied by delta of t minus nts. So this is as sample signal. So now we will take the Fourier transform of the sample signal. Becomes as, so we know that multiplication in time domain reflects convolution in frequency domain. So when we will take the Fourier transform of st mt on summation of delta t minus nts. So means mt delta minus nt minus nts, that is the convolution of two signals. Okay, so convolution of two signals, sorry, some mistakes. Let's, after taking Fourier transform, it will become mf convolution with summation of Fourier transform of delta t minus nts. Okay, so we have seen earlier that the Fourier transform of this is Fs summation of delta f minus nfs. So mf, this is mf, f is delta n. So we know the basic property: when impulse signal convolve with any signal, it results the signal itself. So if you do any shift in delta function, then shift will come into masses that second function. Okay, so we will use that property, and we will get Fs m of f minus nfs. So after multiplication, we have seen that first we will multiply, and we use the convolution property. Multiplication time domain reflects convolution frequency domain. Now we have seen that this converted into m of f minus fs. This is nothing but only the shifted version of frequency spectra of measure signal. That is, we have seen earlier that the frequency spectrum of mt, that is mf, was max fs to fs. So this is the summation of all the shifted version of frequency domain representation of message signal. So now we will draw this spectrum, and now we will see how we reach to this criteria. That's called Nyquist criteria. So we can write this. So what we have discussed earlier, we have seen message signal, we have seen impulse train, then we multiplied both signals, then we see that frequency spectrum of both, then we find that final multiplication of both time domain signals in frequency domain is nothing but only the shifted version of message signal in frequency domain. Okay, so now we will discuss about the Nyquist criteria, and first we will discuss about the spectrum of sampled message signals. Okay, so we get that Fs M of F minus N Fs summation n is equal to minus infinite to infinite. So the spectrum of MF is this minus Fs to Fs, and so this spectrum is nothing but addition and shifted version of MF. So this one is first one for n equal to 0 will same as at z is Fs. Now we will discuss earlier later why we are taking gap. So this is sorry this is Fm, this is Fm, and this is also Fm. So and this is the Fs, P spectra Fs. So this is also Fm, this is also Fm. Okay. So this is the sample signal. Okay, we can see this is the sample signal. So this is the band gap. So why this band gap is important? So suppose we want to reconstruct this signal at receiver end. So we will use a filter, low pass filter. This is the practical filter. In ideal filter, we generally use sharp edges, but in practical filter, there is no sharp edge. There is a falling edge here. Okay. So suppose this is Fs, this is Fm, this is Fm. So from 0 to Fs, we can see that this is Fm, this is Fm. If Fs is equal to 2Fm, then this spectrum will be like this. This is called actually ideal sampling. So for reconstructing this type of sampling, we have to use ideal low pass filter. But generally there is no such type of filter. So next we will see that if Fs is less than is equal to 2Fm, here we can see that if Fs is less than equal to 2Fm, then situation will be like this, and interference will be occur, and this interference is called as aliasing effect. Okay, aliasing effect. So that's why this criteria is important. If we will choose Fs less than equal to 2Fm, we will face such type of condition, that is aliasing effect. So that's why it is very important that Fs must be greater than 2 times of bandwidth of master signal, and that's why we choose this sampling frequency, because by choosing this sampling frequency we can get master signal without any noise, without any deconstruction. That's why we use this criteria. So it explains that this criteria Fs greater than equal to 2Fm. Okay, Fs is greater than 2Fm. This is the practical case, and generally we use this criteria. This is called ideal sampling. This is called undersampling, and this is called oversampling. So we have seen that by using the spectrum of master signal, that this is very important to choose a sampling frequency greater than equal to 2Fm. So that's why we can reconstruct the data without any reconstruction. Okay. So that was the sampling theorem. Thank you very much.